Our topic for today is called Python Beyond the Usual, Building a Remote Control Car with MicroPython. Couple of words about myself. So I am working in IT for the last 10 years, and I always worked very close with the hardware. So I worked as a test automation engineer, as an embedded engineer, software engineer for test stations for manufacturing. I was a team lead for that direction, and now I'm again working with manufacturing. And during these 10 years, I always did some pet projects, side projects, mostly related with the hardware, and this one is a good example. Feel free to connect my social networks. Sometimes I post something about my projects. I don't post anything about the leadership, so it's free to open it. And let's get started. Here is the link to the slides. I will share some link on the slides about particular topics. So, and if you cannot see them well, feel free also to open them. I gave access to everybody. So our plan for today is following. We will talk about microcontrollers, understand what does it mean. That's mostly related to the hardware. Then we will make a short introduction to MicroPython. That's more a software topic. Then we will go back to the hardware and we will overview a key component that we need to build a remote control car. Then I will show some pictures how I assembled it. Then we will go through the software of the remote control car, and then I will show it. And the last bonus part is comparison of MicroPython and C code. So what is an MCU? What is a microcontroller? You can think about it as about a small computer. So microcontroller has everything integrated on board. That means that you cannot order a microcontroller without like RAM or without memory. Everything is inside. And the key difference between normal computers and microcontrollers is peripheral devices. So microcontrollers have what we call pins, mostly something between 20 and 48 pins. And these pins can execute particular features, they can do particular job. And also microcontrollers, they consume significantly less power than traditional CPUs, which make it possible to use them for applications where you have a battery and when you need to save power. And also they are pretty much cheap, so for a couple of bucks you can buy something on a well-known websites and start your project. Here I put a comparison between a modern Core i5 PC, Raspberry Pi Pico, which is our today's hero. I also brought with me some hardware stuff, so I can show you microcontrollers and other PCBs. So our today's hero is Raspberry Pi Pico, this one. And we will also compare it with Apollo Guidance PC, which is a PC used to land on the moon. And with the first revision of IBM PC used on the space shuttle. And we will understand the difference between what we can obtain right now for a couple of bucks and what was the most outstanding PC like 50 years ago. So Raspberry Pi Pico has 2 cores, and these 2 cores can execute 2 threads. Comparing to Core i5, it has 6 cores, and they can execute 12 threads. Like, I want to say that Raspberry Pi Pico is a pretty much powerful microcontroller. Mostly they have 1 core. And 50 years ago, computers had only 1 core and 1 thread. Let's compare the frequency of the processor. So Core i5 can work like with 4 gigahertz, and Raspberry Pi Pico can work on a frequency 133 megahertz. And you can compare these numbers to the numbers from old computers. So we have 100 times more frequency that we had 50 years ago. In terms of RAM, for instance, my laptop has 16 gigabytes. Raspberry Pi Pico has only 264 kilobytes. But it is comparable to what old computers had 50 years ago. And regarding hard drive storage, again, my laptop has 500 gigabytes, and Raspberry Pi Pico has only 2 megabytes, which is again comparable, for instance, with memory of Space Shuttle PC. Here are a couple of popular examples of microcontrollers. So on the left side, you can see ESP8266, and the next one is ESP32. I love these microcontrollers because that's where two first available microcontrollers with Wi-Fi and Bluetooth integrated on the chip. And the next one is very popular Arduino Uno. It's Atmega microcontroller that was like a revolution, I would say, 10 years ago when Arduino platform appeared and all these libraries appeared for popular sensors. So it was a revolution for DIY people. And the last one on the right side is STM32. It's also known as Blue Pill. It's kind of like cheap version of the microcontroller without Wi-Fi, but it's very, very usable for the projects. As I mentioned, our today's hero is Raspberry Pi Pico. It has 40 pins exposed, and the way, if you never worked with microcontrollers, so each pin can execute particular functions. Like the most popular function is GP, like a general purpose input-output function. It's shown as a green text, right? And also part of the pins can support some different functions like ADC, SPI, I2C, UART. So you can take a look at the picture, like at the pinout of your microcontroller, and you can easily understand like what pins you can use for what purpose. So what does it mean you are working with microcontroller? Mostly you will use low-level languages like assembler. Assembler is used mostly like during the hard production and not really often, I would say. Mostly it's done with C, C++ programming languages, and your typical workflow is following. It's not like with Python. You write the code, then you need to compile it with a tool chain which has cross compilers, and then you flash this code to the microcontroller, and then you can like debug it. But today we will do this differently. We will program our microcontroller with MicroPython. So the next logical question is, what exactly is MicroPython? So MicroPython is a lightweight version of the Python interpreter, but for you it's still the Python. It looks like a Python. You don't have to compile your code. The only thing you need to do is to download MicroPython firmware from the website, and you need to upload it to your microcontroller. I have to mention that MicroPython is not supported for all the microcontrollers in the world, mostly for most popular, and there is also a restriction, like a memory restriction. For instance, the Blue Pill microcontroller I shown before, it has not enough memory to support MicroPython, and it's officially not supported. So now let's connect UART. So we are using Picacom to do this from the command line, and you can see that we can play with interpreter, we can assign variables, we can call functions, we can create classes, we can raise exceptions. So basically that's all we need for today. That is an execution of the help function, and you can see that help shows you microcontroller specific information. Mostly it's from machine module, and this module it has classes to work with pins, with like PWM, with ADC. So we will use it today. Like I did a very short introduction. Like officially MicroPython supports Python 3.4 version and some stuff like ported from older version, but there is a lot of information with this link, a lot of pages where it is described properly. We also need to know a little bit about MP remote utility. So because now we just worked with UART, with the command line. Of course, that's not what we want. We want to write the code into the file, and we want to upload this code to the microcontroller. And MP-Remote does exactly that for us. So that's our way to communicate with microcontroller running MicroPython. We can copy files, we can delete files, we can create directories on the microcontroller memory, all of that with MP-Remote. That's how it looks when we want to show all the files on the microcontroller. When you work with microcontrollers, there are a lot of hardware-specific topics, and we will touch only a few amount of them, like GPIO input-output feature, PWM signals, ADC, but there are a lot of more, like interruptions or interrupts, like digital analog conversion, a lot of protocols like I2C, SPI, CAN bus, UART, we can use timers, but we won't touch it today. So GPIO is the basic thing. So the idea is that we can use pin in two ways, as an input and as an output. When we are using it as an input, we're just reading the voltage we have on that pin. It can be like a high voltage and it can be a low voltage. And for the output, we can set this high voltage and low voltage. So that's how we can program it. Basically, we just blink LED, and here in the video, I recorded with exactly the same code. So there is a LED connected to this pin 25 on the PCB. But of course, you can connect external LED. Okay, the next one is PWM. PWM means pulse width modulation, and the idea is that this thing has two parameters. First one is the frequency, and the second one is the duty cycle. So the frequency 50 Hertz means that we will generate a periodical signal and we will have 50 periods per second. And the duty cycle means how much of the time from one period we want to have logical 1 and how much time we want to have logical 0. So 50% of duty cycle means that we will have 50% 1 and 50% 0. 75% means that we will have 75% of time logical 1. But in MicroPython, we don't set percentage. Instead of that, we have 2 bytes. 2 bytes is this U16, it's 16 bits, and the value is 65K something. So we have a better resolution to set up our duty cycle. The next thing that we will use today is ADC, analog digital conversion. So the trick is that we live in a physical world and we have continuous signals, but microcontrollers, they work with numbers, and let's imagine that we have a temperature sensor that generates the temperature in that room, and depending on the temperature, we will have different voltage level. And ADC does exactly for us this conversion from analog value to digital value. On that picture, your resolution from ADC is 3 bits, and you can see that we lost a lot of information during this conversion. But in MicroPython, we have 16 bits. So again, the same 65K values. So we have 65 values between our what is called VCC 3.3 volts and 0. So that's pretty good resolution. Now let's overview key components required to build remote control car. So the first component is the transceiver. So this component allows us to transmit and receive information using a radio channel. It uses 2.4 gigahertz bandwidth. So this bandwidth is open. For instance, our access points work in this bandwidth. And our transceiver is NRF24L01. It's pretty much affordable one. And we can think about the usage of this transceiver, that on our car it will work as a receiver, and on our remote control it will be a transmitter. So it will transmit the data to the car. In reality, that's not the true, because this transceiver is smart, and the transceiver knows when we send successfully the information to the receiver, and it receives some like acknowledge from the receiver. But for the simplicity, we will say that one is transmitter and one is the receiver. So we will go with the car first, because transceiver is shared component between car and remote control. This is not related to the Python, it's just a frame. So I decided to not reinvent the wheel, and I just ordered this thing. These are 2 plexiglass plates with 4 wheels, and each wheel is connected to the motor. So let's talk about the motors. Like, I think you have seen this motor. It's like the cheapest brushed DC motor. It produced in billions of samples. The official name is 130 type. It works in the range of voltages 1.5 volts to up to 6 volts. I recorded this video for you. So what I have here, I have my power supply, and I can choose the voltage of the output. And directly to this power supply, I connected my motor. So let's see how it works. So I think you got the idea. So the more volts we apply to the motor, the faster it will rotate. Oops. But it's not very convenient to communicate with the motor directly from your microcontroller, because motors, they need a high current, and microcontrollers, they cannot supply it directly. And also, motor driver gives us a benefit, which is an interface. And this interface is super convenient for the microcontroller. So we have GPIO pins to choose the way our motor will work, and we have PWM signals to choose the power of our motor. And we will use today this MOSFET-based motor driver. Like this one is power efficient. For instance, there is an old one. It uses bipolar transistors, and you can see this huge radiator mounted on top of the driver. And this one is kind of efficient. There are 2 links here. I highly recommend to check them if you are interested in this topic of motor drivers, how to control them, and all of that. Let's take a look at the pinout. So on the left side, we have blue text and green text. These 2 pins, like blue pins, they should be connected to the first motor, and 2 pins in the green box should be connected to the second motor. So this motor driver works with 2 channels. And to control the driver, we have pins on the right side. Again, we have separate pins to control the A channel and B channel. To control one channel, we need 2 GPIO pins, and we need 1 PWM pin. This table shows combinations of 2 pins. So there are like 4 combinations, and this value is converted to the way how we want our motor to operate. So there is an off state when motor driver does not work with the channel. Forward, when we want our motor to rotate in the forward direction. Reverse, which is in other direction. And brake, when we want it to stop. And as I said, PWM signal helps us to control how fast our motor will rotate. Like when you are doing DIY projects, sometimes you don't use like power supply, like a battery or something, and you power on your system from USB cable from your PC, but that's a car, and we need a proper power source mounted on the car. So sometimes people go with set of AA batteries or AA accumulators. Like I decided to go with a proper lithium battery for the better performance, and this battery can work for maybe 4 or 5 hours. So our car can work with that battery for 4 or 5 hours or even longer. But if you will ever try to use that battery, so don't connect it in the beginning of your development process, so you need to check that you don't have shortcuts or other problems, because these batteries are really dangerous. If you shortcut it, it can make a fire. The battery provides 11 volts of voltage, but we have different components, and different components, they need different voltages. Like microcontroller has a voltage regulator installed, and it can work from 1.8 to 5.5 volts, and motors require 1.5 till 6 volts. But it's better to separate power lines for microcontrollers and other electronic devices and for the motors, because motors create a lot of noise when you work with them. So for you, that means that sometimes your microcontroller will just reset without any reason. So basically, our task is we need to step down our 11 volts to have like 2 separate lower voltages. And to do this, we will use a PCB, which is called buck converter or step-down converter. I have chosen Mini 360 buck converter. So the idea is following. You have an input range and you have an output range. And output range is always lower than input range. And you can adjust that voltage with a potentiometer mounted on this PCB. We will install 2 of them on our board. And again, another link with another great resource about different ways how you can step up, step down, how you can regulate voltage. Very useful. So now let's go back to the remote control. So the remote control will have the same microcontroller, the same buck converter, but only one of them, the same transceiver. We will power it on from just 4 AA accumulators. And one more component would be a joystick. So let's take a closer look at the joystick. It supports 2 axes, X and Y. Can be powered in a small range between 3.3 and 5 volts. And the idea is following, like you change the position of the handle, and depending on the position, you will get from 0 volts to like 3.3 volts in our case. We will install 2 of the joysticks on our remote controller just for convenience. You can do this with only 1 joystick, but it's very hard to control the car with 1 joystick. Okay, now we will assemble the car. So here we received our frame. Here we soldered wires to the motors and assembled everything on the breadboard. We checked everything on the breadboard, and after that we decided to solder the debug board. Here you can see an example of bad engineering that I did. Like after I assembled everything, I've discovered that I cannot connect USB cable, and I flash my microcontroller. Here is our car with the debug board. And here is the first version of the remote control. So I just mounted it on the wooden plate. Like at some point in your projects, you will face a wiring problem, which means that you will have, I don't know, like 40, 30, or maybe 50 wires connected everywhere. And you can live with it, but the problem is that if you left your device on the desk and, for instance, your kid came and just touched it, something will be disconnected, and it's very hard to find what exactly is disconnected, and you spend a lot of time on that kind of troubleshooting. So I decided to trace a PCB. How it works, there are a lot of software to do this. I have chosen KiCad software, which is open source, and it works with Linux. So the first step to design a PCB is to create a logical schematic. So you have to connect everything and understand how logically your PCB will work. And the next step is to trace everything. So also I did a PCB which can be used for remote control and for the car, because when you order it in China, you cannot order only one unit, you have to order like 5 at least or more. So I just wanted to save a little bit of money. Here is our PCB. I also brought with me an example of that PCB. So like it could be smaller, but I did it so big because it's convenient to control it when it is a remote control. Also, I did a mistake during the tracing, but it's fixable with soldering station and with a cutter, and I fixed it in the next revision. Here you can see the difference in our remote control. Like here I connected the battery pack. I decided to do one more step, and I used a laser cutter to cut from plexiglass a case to my remote control to isolate things, and it's like more convenient to control it like this. Also, there was no place to mount a battery pack, but with plexiglass, it works just perfect. Here is the car, and you can see that there are almost no wires. You cannot get rid of these wires because these wires, they are coming from the motors. And the goal of PCB is exactly to reduce all these wires because the tracing is doing this inside the PCB. Okay, now let's move to the software part. So our architecture for the remote control and for the car would be super simple. We will implement what is called the main loop, and then we will call run method, and this method will run forever. So the transceiver code, I forgot to mention that MicroPython has something like a standard library. So this is a set of drivers, set of like examples for popular like sensors, and I discovered that this transceiver already had a driver implemented, so I just reused that driver from the MicroPython itself. It uses SPI under the hood, so we just create an instance of a class, and that's it. It has also support for, as far as I remember, like 100 channels, RF channels, so I have chosen just random one. The transmission is straightforward. We have 2 Python values, and we pack them into the C structure as 2 integer values, and that's it. Send it using the driver. If something did not, like, I mean, if the package was not delivered to the receiver, then we will get an exception. And that's how we know from the driver that something did not work. We don't have a receiver. The receiving part is, again, with driver, super simple. We check that we can receive something, then we receive it, then we unpack it from the C buffer, and that's it. The joystick part. The joystick code is super short. First, we need to create 2 instances for 2 ADC channels. We also have 2 LEDs mounted on the PCB, one to indicate that our code booted up successfully, and the second LED shows that we actually are doing something successfully with receiving or transmitting the data. It's called radio LED. And the loop is like several lines. We just read from ADC values, and then we send them to the driver, and we indicate the result with radio LED. The car code. So first of all, we create like a data class for our motor driver. Like we have 2 channels, that's why we have this directions and duty cycle. This data class we needed just for ourselves to understand better. It's like an intermediate step. So intermediate step between receiving the data from remote control and applying it to the driver. So this class represents the state of our vehicle. We have like left side and right side. So like our car has 4 wheels, but we will operate left side together and right side together because we have 2 channels, and that's how we can control where our car will move. The motor driver, like that's just a preparation of all this pin. We just initialize all of them, like create PWM pins and assign 0 value initially. Here this is almost like an implementation for the table I shown before, but we do an opposite conversion. We have a direction, and we need to understand how to assign pins according to this chosen direction, like forward, reversed, or off, or brake. This is a part related to the motor driver. Again, two functions: initialization, where we want to stop the driver, and the run function, where we get the data from the driver data class and apply it to our pins. The main loop is similar to what we have seen for the remote control. There is one more thing that is very useful, like your Python console is connected to your USB port, but it's not super convenient to keep this like USB cable connected because it gives power to the PCB, and when you have these power management boards, sometimes they start overheating because of that. And it makes sense to just duplicate everything from a MicroPython to a separate UART. That's what we are doing in the line 19 and 21. The run method, so basically we are keeping to call our loop function with a period something like 10 Hz or 20 Hz. So this one is the most important, like loop function. We receive the data from the joystick. Here we have like two choices. If we didn't receive the data, then at some point we need to call a timeout protection function. So timeout helps us to stop the vehicle, for instance, if our joystick died or something went wrong. And if we did receive the data, then we do our conversions from the values from our joystick to this intermediate state I mentioned, which is called engine power, and then to the driver data class. So that's all we are doing in the loop function. Timeout protection just stop the driver, that's it. Now we need to understand one concept related to the hardware. So if our joystick is in some neutral position, it does not mean that it will produce for us the value 32K768, which is a center of this like 16 bits, because there is a noise, and this noise is quite big, and this noise, if we just keep it, it will affect the behavior of our car. So here I call that concept a dead zone, or we can call it like a hysteresis. So the idea is that we do the simple filtering, like we get this center value and we say that all the values around this center, like plus 10%, minus 10%, they are 0 for us. So we just ignore them. And another important thing is this turn coefficient, line 14, 0.6. I will explain it a little bit later why we need it. So we start our conversion. We have two values from the joystick, and we have two other variables, turn and forward. Forward represents the movement forward, and turn represents how we want to turn, like if it's positive into one direction, if it's negative to another direction. And we start with applying this dead zone concept. We ignore all the values around the center. And then we move these two values, because initially it was 0 to 65K, we wanted to be something like minus number, plus number, and with 0 in between. We do the same with y-axis, and in the end of that slide, we have forward and turn values in range minus 100%, plus 100%. Now this part with turn coefficient, like why do we need it? It's kind of like a magic number. Like, let's imagine that we don't have this magic number and it's just 1. We have our joystick and we put it into the right top position, which means that we want our vehicle to move forward with 100% power and like to the right with 100% power. So that means that we start with applying this forward movement to both sides of our car, and we have left side 100% and right side 100%. Then we apply this turn value. So we should apply it with different signs to our sides. That's how we will get this rotation, right? This movement. And let's imagine that we have turn coefficient 1. Like for the left side, it should rotate faster, and right side should rotate slower. We will get for the left side 200%, and for the right side we will have 0. So that means that our right side will do nothing, and the left side will try to move as fast as it's possible. But that's not the movement you expect from the car in that position of the joystick. But with that coefficient, we will have right side 40% and left side 160%. Of course, we will limit these values within -100, +100, but we will achieve the expected movement. And we will do the last conversion where we convert this engine's power into the driver data class. Here I used, I created a function inside the function, and it works in MicroPython. So it's time to run our car. So it works. I don't want to spend time right now on that. If we will have the time after the questions, we can play a little bit more with that car. Because I have the bonus part with comparison MicroPython and C, and also one more video that I want to show you. So I will turn it off for a while. So what I did here, I tried to implement 4 similar tasks with MicroPython and pure C on the same microcontroller, Raspberry Pi Pico. It was the same one, like hardware, piece of hardware, to avoid all the problems that like hardware was different and all of that. I executed the code 10 times for both C and MicroPython. Here is the repo that you can check. And these 4 tasks were calculation of the factorial, calculation of the summation, 3x3 matrix multiplication, and GPIO blinking. So here is the C code. Here is the MicroPython code. So factorial is calculated from from 0 to 20. Here are the results. So the difference in execution time is 168 times. So MicroPython is 168 times slower than C, and the timings for MicroPython, they are like distributed a little bit more. So that's true not only for this example, but for all the examples. Like C code gives you like almost the same timing, like almost every time. But with MicroPython, you have a distribution in timings. 168 times slower. The next one is summation from 1 to 1 million. Here I did a mistake. I used some function, so I gave some kind of advantage to MicroPython. But here are the results. Again, MicroPython is 166 times slower than C code. Blinking, this one surprised me more than other examples, because like I expected that they will give some kind of similar results, because what is a blinking? We just calling like functions to go to the registers and put the right value into the right register. But there is a difference. And the difference is 445 times. Of course, MicroPython is slower. Matrix multiplication, why I decided to do this task, because maybe you want to implement some kind of robot, and for that you need to multiply matrices to, to convert from one XYZ to another XYZ, so it's also useful. I implemented it with 3 for loops, like in the most straightforward way. MicroPython is 800 times slower than C code. So here are examples altogether. There is no big surprise that MicroPython is slower. My conclusions. Like, if you never worked with the hardware, I can say that there is a lot of fun doing that. It's not super expensive today. As I mentioned, like you can purchase a microcontroller for a couple of dollars, and basically like the whole cost of the car is maybe like, depending on the battery, like the battery is the most expensive part, but something like 60 or 70 euros. Like, but you can save money replacing lithium battery with just 4 AA accumulators and all of that. So it's very affordable. If you worked with the Python, the MicroPython is almost the same. You just need to maybe learn this one more library and that's it. You don't need to have like special knowledge. If you are an investor and you decided to use your like Python developer and to deploy 1 million of devices with MicroPython, I don't recommend to do this because your competitors, they will save BOM, they will save money on purchasing the cheaper hardware, but they will deliver the same level of performance. But in the same time, MicroPython is not only for toys. During my job activities, I did a project that works 24/7 on ESP32 microcontroller, and it solved our problem. We have maybe like 30 or 40 setups running on the daily basis. I don't see any problems, but I did not care if the execution took like microseconds or milliseconds or even seconds. It did not matter for me. So that's it from my side. Several links, social media, performance comparison, Python code, and the last link is my original FreeRTOS code, because I started to build this car with the same hardware, but with C and FreeRTOS. And this implementation is a simplified version of what I achieved with my C code. So if you are curious, you can also check that link. There is a lot of code there. Thank you.